implicit differentiation stuff. So, right, the central idea to it is, let me take a really silly example. Well, actually, let me write it this way. Something like that, right? Super, super easy. And if I asked, what is dy dx, you guys would all say 2x, done. Okay, right? So this is easy for a couple of reasons. One, x squared is a pretty simple function, okay? And two, when I write y equals x squared, this is what I would call explicit, in the sense that one variable is completely expressed in terms of the other. The relationship between them is explicitly given. Now, if I rewrite that equation like this, okay, now instead of a function, I have an equation, all right? And in this case, I would say that the relationship is implicit because I have a relationship between them, but it's not one variable in terms of the other. We going to live back there? Okay. It sounds like death was imminent. Okay. Yeah. All right. So now, in this case, right, me taking y minus x squared equals 0, like I could easily solve that for y back in x squared, right? So in this case, it was super easy to move back and forth. And, but let's pretend that we didn't, okay? So here, if we're going to think of this implicitly, I'm going to think of y is really a function of x. I just don't necessarily know the formula. Now, in this case, I clearly do know the formula because we're not morons. But in some cases, it's either inconvenient or outright impossible to get an actual formula that you can write down. Let's just pretend that y is a function of x whose formula we do not know. All right, so if I take the derivative of both sides, well, let's work from the right to the left. The derivative of 0 is 0. That's easy. The derivative of x squared, or minus x squared rather, is minus 2x. And then what's the derivative of y? Okay, so here's where we got to be careful. Okay, 1 would be a valid answer, except what's the difference between y and x? Like if I asked you what's the derivative of x, you'd better say 1, right? But what about the derivative of y? Well, it's dy dx. I don't know yet, right? So y is some function of x whose formula I either don't know or have forgotten. What's the derivative of that? I don't know, dy dx. Or you could write y prime, okay? Now, my preference is to write dy dx instead of y prime. And the reason is that y prime looks a whole lot like y to the first. And yeah, you don't want to make that mistake, okay? So I typically will write dy dx instead of y prime, even though they're equivalent, right? So it's just, you know, I've noticed over many, many years that sometimes the student is doing a problem perfectly correctly, and then halfway through, y prime becomes y to the first, which just becomes y, and then things kind of go downhill from there, right? So, right. Okay, now, if the original goal here was to solve for dy dx, can I do that now? From here, I've just got to pop the 2x back over to the other side, and now I have dy dx equals blah, right? Okay, so that's sort of the crash course, right? The idea of implicit differentiation. Just think of y as being a mystery function of x and obey the chain rule, right? That's why it's y prime and not 1. Now, this, like I said, was a super contrived example because we didn't need to do this thing implicitly, right? We could have done it explicitly, and that would have just been as easy. Okay, but let me take an example where doing it either way, actually, there's benefits. Okay, so let me, for the sake of space, let me go over to a new sheet. Are we good on... good to move on? Okay. All right, so let's take an equation. And normally, implicit differentiation problems, you start with an equation rather than a function. Because if you had a function, you wouldn't need to do it implicitly anyway, so, right, okay. This also is a bit of a historical thing. So the idea of an equation is much older than the idea of a function. And it wasn't really until, say, Euler that people were kind of thinking about functions in some sense. It was much more common to think of an equation, and you would then find the slopes of tangent lines or whatever of that equation rather than of that function. Okay, so first off, let's do this the explicit way. Now, the only problem with doing this the explicit way is, do I have y in terms of x? Not yet. Could I get it that way? Sure. And what would be the equation? Am I missing something? I am. Yeah, okay. So technically I would need a plus minus here, and so it's really two functions, but right. And what is the graph, by the way, of this equation? Yeah, it's just a unit circle. Okay, so I need the plus minus because the plus describes the top half of the circle and the minus the bottom half. Okay, so if I took the derivative of this, well, first off, how do I have to write it? Right? Square root of something is really the same as raising it to the 1/2 power. Okay, so then I can pop the coefficient out front, leave the insides alone, take 1 away from the power, and multiply by what? The derivative of the inside, which is? Okay, like so. Okay, so I just did some quick, fastest chain rule this side of the Mississippi. But, yeah. I had chili for dinner last night. I didn't make the chili. I bought it at Four Seasons in town. It was pretty good. She used pulled pork instead of beef. Okay, fine. A little different, but okay. But you know what it had in it? The chili? It had black beans in it, which I happen to like. But the presence of beans in chili is a hanging crime in most of Texas. So, right. And spice and tomato. And preferably lots of it in the spice department. All right, so, but Texas is on the other side of the Mississippi. I have to say it's kind of weird living east of the Mississippi, but whatever. Okay, so we can simplify this a little bit because the 2's cancel, right? And then we've got a negative exponent, and it's a -1/2, so that means the square root in the denominator. And then the last thing is I've got a minus times the plus minus. So what does that give me? Well, not necessarily. If it's minus, I get a plus. But if it were plus, I would get a minus. So this brings me to one of my favorite symbols in mathematics. Not plus minus, but rather minus plus. It's like plus minus, but backwards. I'm not making that one up, okay? Huh? Because, like, let's say that you have a formula where the pattern is like one of them's plus, one of them's minus, and they have to be opposite of each other. If you just write plus minus, it's not clear which one is opposite of which one. So we have the minus plus symbol basically so that you can encode and make clear when this one's plus, that one's minus, and vice versa. Yeah, not just to make up a cool symbol, which is, kind of fun too. Okay, so anyway, that's what we get. And perfectly fine, right? I could, plug numbers in, get slopes. Now, I guess one other thing to think about is if I picked a particular point, I have to choose correctly between the plus or the minus version of this. How do I know which one to pick? Yeah, if whether or not the point I've chosen is on the top half or the bottom half of the circle, right? And so I would need to know where I am in order to correctly pick the which equation I used, and then therefore which slope. Okay. Now, if we do it implicitly, we don't have that problem. Okay, so step one, take the derivative of both sides. And then what's the derivative of 1? 0, that's easy. What's the derivative of 2x? Or, x squared, sorry. Freudian slip there. 2x. All right, now, what's the derivative of y squared? Careful. 2y dy dx. Okay, now why is it that? Okay, why did we have to multiply by dy over dx? What? The chain rule. Y is a function of x. I just don't know its formula. Okay, so for the same reason that I multiplied by minus 2x in the explicit version, I have to multiply by the derivative of y here. I just don't know. Well, better late than never. That's all right. We'll save the beating for next time. And I've got this thing. I could make you go out into the Arboretum and pick your own. Huh? Yeah. I guess we're not allowed to talk about Bill Cosby anymore, but he did have a good routine of you get sent out into the backyard to pick your own stick, and if you pick too big of one, then you're going to regret it, and if you pick too small a one, you're going to get sent back out, and anyway. Okay, so that step there is the calculus over with. Have we completed taking the derivative of everything? Yeah. So now what are we left to do? Well, what were we trying to do? We were trying to find dy dx. Can I solve that equation for dy dx algebraically? Yes, okay. And what's it going to be? Negative x over y. Okay. Now, that answer may seem unsatisfying. And in what sense is it unsatisfying? Yeah, there's still a y in it. Okay. Now, and many times that's going to be the case, right? Your answer will still have y in it. In this particular case, do I know what y equals? I do. It was up here, so I could substitute it in there. And get exactly the same thing as we had the other way. Okay. So in this case, I knew what y was in terms of x. Not always do I have that. But in this case, I do, okay? Right, so sometimes it's a super pain in the butt to do this explicitly. All right, so this is a circle, so let's pick a point on the circle. So give me an x coordinate at least. Okay, give me an x coordinate that's between -1 and 1. Okay, so it has to be that because the radius of my circle is too small, so it would never get that far out. Okay, so 1/2. All right, so if x is 1/2, y is what? Well, it'd be the square root of 1 minus 1/4, right, because a half squared, would be √3/2. Okay? That coincidentally, if I were to sketch this, what angle is there? Thank you. Or in radians for the 360 no scope. Yep. What, am I not allowed to make gamer jokes? Yeah. I was gaming when you kids were in diapers. Okay, so. All right. So if I were to draw the tangent line at that point, I mean, subject to my crappy art skills, what does it look like the slope is? Well, clearly negative, right? That part's the obvious. So what is the slope? Well, what would I need to do? I need to do -x over y. And if I simplify this, then it'd be -1/√3. Okay, or how many of your high school teachers got all like spazzy if you had square roots and denominators? Yeah, I to this day do not understand what their problem is. It's just a number. It's in a denominator. Who cares? Right? Believe me, we have bigger fish to fry. So -√3/3 if you prefer to have to have it rationalized, or -1/√3. Okay, same thing. All right, does that seem reasonable given the graph? Okay. All right, so let me flop over to Mathematica here, and let's take a look-ski. Okay, so what I'm going to do is, the first thing I'm going to do is I want to plot my original circle. Now, in Mathematica, and let me come down because of the stupid light, if I want to use so every time so far that I've used the plot command to graph things, I was using it because I had a function. Here, I want to think of how do I plot an equation? And the way that I do it is not with plot, but rather contour plot. And contour plot, I need to specify two ranges, the x range and the y range, okay? But this function allows me, the contour plot function, allows me to graph an equation rather than a function, okay, which is handy. And, not shockingly, I get myself a circle. Big surprise, okay? Radius 1, centered at the origin, everything's cool. All right, now, what was the slope that I got for my tangent line there? -√3/3, okay? So if I were to write an equation of the tangent line, what would it be? Y minus the y coordinate equals slope times x minus the x coordinate. Yeah? Okay. Now, could I rewrite that thing in y equals form? Yeah, totally. Okay, but deliberately here I'm not, just to demonstrate the use of the contour plot function. And then I'm going to plot this thing on the same range of x and y that I did the other one, so that I can layer the two graphs on top of each other. Okay. Now, the other thing. Does it bother anybody besides Owen that I have double equals? Huh? Oh, right here. You probably didn't see it. So if I type it, equals, equals, right? And then if I move the mouse away, it'll sort of collapse them. Yeah, okay. So what's the difference between double equals and equals? This is a computer thing. Okay. So, yeah. Whereas single equals is assignment. Yeah. Huh? Yeah, exactly. Okay, now in this case, it's maybe a little bit less clear why we need to worry about that, but in the computing world, typically, using single equals sets the value of something to be something else. So if I set x equals 7 or whatever, I would use a single equals. If I want to then check, is it true that some quantity equals some other quantity, I use double equals. And that's just, it's been that way for God knows how long in the computing world. And so here, anytime I have to type an equation, and thinking of it as an equation, I need double equal instead of single equals. Okay, so that's partly a Mathematica thing, but it's like that in basically every computer language. Okay. All right, so great. Now, first off, then, is it clear? Why is that the equation that I wrote down? Okay, so let's make sure we have all the parts in the right places. Okay, what am I using there? Point slope form. Okay, y minus the y coordinate equals slope times x minus the x coordinate. 1/2 was the x coordinate that Mr. Amore chose, and then we found the y coordinate that went with it. Okay, and if I graph that, then there we go. Okay, now I can put these two things on the same graph, however, by just, well, there's two ways to do it. Well, first off, let me do, or I have to do contour style here. Okay, there we go. All right, now, when Mr. Amore picked x equals 1/2, and I solved for y, we got √3/2. But isn't there a second point that also would have worked? Yeah, negative √3/2, which would have been down here, and what would have that slope been in relation to the slope of the red line? Yeah, just the negative of it. Okay. It wouldn't have been like the negative reciprocal. That would have been if they happened to be perpendicular. But yeah, and the reason it would have just been the negative is because what was the formula? What did we get for dy dx? It was negative x over y. Well, if I negate the y coordinate, then that just negates the slope in that case. Okay. All right, so does that kind of make sense? Right, for the circle? All right, good. So let's go on to one that's maybe a little bit spicier. So flip over to the second page of the sheet, and let's look at that one. Okay. Or those two. Okay, so we've got this equation here, x cubed plus y cubed minus 6xy equals 0. Okay, and this thing happens to be have a famous name. It's called the folium of Descartes. This, I have to say, this section is one of my favorite parts of teaching Calc 1 because typically you're using an equation rather than a function, and there are lots of really interesting equations that have people's names attached to them that have lots of historical stuff going on. And this one's certainly no different. All right, so just for edification, let me plot that thing. Okay, and let me kind of blow it up a little bit more. Okay, so it's this sort of leaf-looking thing, and it is certainly true. So let me throw in one other thing here. Oops, I need to scooch it. I'll have to scooch it down, but there is an asymptote there, and a straight line. I just need to scoot the equation down a little bit. Okay, great. So let's find the derivative of that thing. So x cubed plus y cubed minus 6xy equals 0. So x cubed, what's the derivative of that? Y cubed. 6xy, what do we have to do there? The product rule, bum, bum, bum. And of course there's a minus out front, so don't mess that part up. Okay, so go through and work out the derivative real quick. And I'll stand up at the front and scowl at everybody. Well, yeah, there's a 6 also. Either way, yeah. In the end, it won't matter, just as long as you keep up with it. Let me see what I did with my pencil. This is like that episode of South Park where, oh, there it is. Okay. Okay, so there's the first couple of steps. Do we agree up to that point? Okay, so as Owen suggested, I pulled the 6 out and thought of xy as being the product. You could have kept the 6 with one of the two terms. Just sort it out and be careful, okay? All right, but do we agree that I've got everything correctly sorted out there? All right, so now what do I want to do? What's the goal? Yeah, I want dy dx equals blah as my answer, okay? So at this stage, what I'd like to do is any term that has a dy dx attached, put on one side of the equation, and any term that doesn't, put on the other side of the equation. In this case, the two terms that have dy dx, well, everybody's on the same side, but I can move them. So I'm going to leave this one here and that one there. And then I'm going to move the 6y and the 3x squared to the other side. Okay, why was that a good move? Yeah, by having all the terms with dy dx on one side, the next step is that I could factor. Okay, and so if I do so, I get this. All right, and then what do I need to do to get dy dx by itself? Just divide by the stuff that's out front of it. And we'll worry about simplifying later. And we get that. Okay? All right, so now, yes, I could go ahead and factor a 3 out of everybody and cancel just to simplify. I'll leave it like this for just because I'm lazy. So that gives me the relationship of the slope. Now, what's maybe interesting here is notice that we have the relationship of the slope, but we still haven't ever solved for y equals in terms of x. Right, that's fine. And if we go back to the original equation, do you want to solve that thing for y in terms of x? You could, painfully, very painfully, but it's not as obvious how to solve that thing for y in terms of x as opposed to, say, the previous example, right? So this is what I meant earlier when I said sometimes it's a real pain in the butt to try and solve for one in terms of the other. This would be a good example of that. And sometimes it's outright impossible. So, c'est la vie. Okay, now, that said, if you pick a particular value of x or y, either one, could we then try and solve for the other one? Okay? Still would be a little painful, but not as bad as the general case. Okay? So, Mr. Amore, pick us an x coordinate here. 2. All right, so if Mr. Amore picks 2, we need to solve their equation for y. Okay, so let's rewrite it. Y cubed minus 12y plus 8 equals 0. All right, if this were y squared minus 12y plus 8, we'd be in business, right? Because then we could just quadratic formula it. Unfortunately, it is not. It's y cubed. All right, so how do you solve cubic equations? Very carefully, yes. Okay. Yeah, that's how I would cube something, not how I would solve a cubic equation in general. Okay, so it turns out, I mean, we could spend an hour doing the algebra here, that this is an example, well, okay, so there's a trick that we could use on this one. I'll spare it, we won't go through it, but this cubic, what do you notice about it? Is it missing something? It's missing the y squared term, okay? And accordingly, cubics that are of that form, we call depressed cubics. Not like they're sad or something, but yeah, that's just a term that we use. And there are some tricks that you can use there. Now, the other set of tricks, do you guys remember doing like the rational root theorem or Descartes' rule of signs or anything like that in high school? No? Okay. The other solution is, well, we've got this really sophisticated program in front of us called Mathematica. Maybe we can just punch it in there and see what we get. Okay? And in fact, just for the sake of time, that's what I'll go ahead and do. So I need to solve the equation y cubed minus 12y plus 8 equals 0 for the variable y. And here's what I get. I get some numeric answers, and there we go. I'm actually kind of surprised it gave them to us as decimals. That's interesting. Okay, but anyway, we get 3 answers. Now, does it make sense that there should be 3 answers in this case? All right, what was the x coordinate that Alex picked? He picked x equals 2, which intersects here, here, and here. So, of course, there should be 3 numbers. Okay? And it would be up to us to, you know, if we knew which one we wanted, to then use the appropriate y coordinate. Okay, now in this case, right, so if I gave you a problem like this, I would pre-select the x and the y coordinate. Okay, unless in situations like this where the algebra is terrible. Okay, all right. But once we have the x and the y coordinate, we can just plug them in and then get our equation, and that's good. Okay, good? All right, so let's look at the next one here, which is, what about if I wanted to find the second derivative? Not the first derivative, but the second derivative. Okay, so first off, let me just write it. X squared plus 4y squared equals 1. Okay, find me an equation for dy dx. See if you play. Okay, so find dy dx first, and we'll worry about the second derivative later. Here's the trick, by the way. So, yeah. You're good? It's kind of interesting that there even is a trick. This is all the rage solving these things back in the day in Italy. In fact, the way that you got a job as a lecturer at a university was to challenge somebody who already had a job to like basically a math duel, and you would come up with a bunch of problems, and your opponent would come up with a bunch of problems, and then you'd exchange them, and then you'd have to solve them, and whoever did better won the job. So, you know, it's sort of like, oh, I can solve a cubic equation. Oh, yeah, I can solve a quartic equation. Yeah. I'm only partly exaggerating. All right, so what'd you guys get for dy dx? Negative x over 4y. You guys agree with Owen? Yep. What is the equation here? X squared plus 4y squared equals 1. If I graph that, what would I get? What shape? It's not a circle because of the 4. An ellipse, yes. The proper term, Mr. Amore, is oval. No, it's an ellipse. So, yeah. Okay, that's great. But what do I really want? I wanted the second derivative. Okay? So, what is the second derivative? What does that mean? Exactly. I take the derivative of the derivative. Well, we've already got the derivative, so let's take the derivative of it. All right, and the second derivative in Leibniz notation is d squared y over dx squared. Does it bother you that the 2's are in different spots? Get over it. Okay, it's just the notation. There's a good reason for it. Well, if I want to take the derivative of that there fraction, negative x over 4y, what do I have to do? Well, what rule do I need? Quotient rule, right? So what does the quotient rule say? Thing on the bottom times derivative of the top. What's the derivative of negative x? Negative 1. Okay, that's easy. Minus thing on the top times the derivative of the bottom. Oh, we got to be careful. What's the derivative of 4y? For y prime or dy dx, right? Man, you're going to be an oval guy and a y prime guy? Yeah, I like that. Just don't mess it up, and we're cool, okay? All right, so low d high minus high d low, all over. Yeah, low squared. Okay, and let's clean this up just slightly because we got a double negative going on there. All right, are we done? No, because I asked a question and therefore we're not done, right? The law of pedagogical predictability. Why aren't we finished? Yeah, what's dy dx? Well, fortunately, we already know that. So I can just substitute what we got earlier in, and then we can simplify a little bit because the 4's cancel. And maybe we could simplify a little bit with a bit more fraction foo, but that's good enough, I think, for now. Okay? All right, so what's the second derivative? Well, I don't know, the derivative of the derivative. And then just kind of work it out from there. All right, Gucci? All right, so the last one that I want to talk about today is what's called logarithmic differentiation. All right, so let's say I have x to the x. and I asked you to take the derivative of that, what would the two quite reasonable but equally wrong answers be? One would be to say, oh, the derivative of something to a power is x times the thing to the x minus 1, right? Okay, why is that wrong? Okay, so let me write it this way. All right, that's what the power rule would say. Why is that wrong? What does the power rule apply to? Yeah? When the exponents are numbers, is x a number? No, it's a variable. Okay, so it can't do that. And if we said, oh, well, this is kind of like e to the x, so maybe it's x to the x times the natural log of x, which is what the e to the x rule would give you. No, that's wrong too, because the e to the x rule assumes that the base is a number, not the exponent. Okay, so we're kind of hosed. Except, if I'm really clever, what's the whole problem here? That pesky exponent, right? Can I just get rid of an exponent? Exactly. It's not like I can call up the mob and put a hit out on him, right? But I can beat his kneecaps with a log. Okay, that one was a bit contrived, right? Yeah, who knew that math was such a violent affair? Okay, so I can take the natural log of both sides, and why is that a good idea? Because what's the log of a thing with the power? What happens to the power? Yeah, it pops out front. Okay, and that is going to be a whole lot easier to deal with. Okay, so I have an equation. I want to find the derivative of it. Okay, so what is the derivative of log y? What's the derivative of natural log of something? 1 over the something times the derivative of the something, or dy dx. Okay? What about on the right? What do we got to do? I'll take product rule for 500, Alex. All right, so what is it for 500, Alex? ln 2. Oh, sorry, look down one. Are you looking at 2 to the x? Yeah. Skip to the next one. Yeah, sorry. All right, so here, we'll just do it. First times the derivative of the second plus the second times the derivative of the first, right? And then I'll multiply both sides by y and simplify. Okay? Could I substitute x to the x back in for y if I wished? Sure, okay? And in this case, I would want you to do that because, we started with a function of x, and so it's sort of satisfying to finish with the function of x. Okay, so does that kind of make sense? So this technique is called logarithmic differentiation. It essentially is the following. If you get a bunch of nasty exponents and products, take the log of both sides. Maybe that'll make your life easier. Do it implicitly, and then there you go. one other little piece of trivia. This exact problem was one of the problems on math comps this year. And you would not believe the bullshit answers I got, including the things from the top right. Okay? It's fortunate that the students do comps anonymously, so I don't know who I'm grading. I just have like a little code number, right? Because if I did know who was who, there would be many, many a stick beating. Okay? Yes. Okay, so, yeah, anyway. All right. That's probably good for now, and we'll continue on Wednesday. And just so we're clear about one piece of business, what are we doing on Friday? Yeah, your next celebration of learning. The chain rule, which is what we did on Friday, is the last covered topic. So what we did today won't be on it. Good? All right. See you guys later.